We take watering for granted without understanding what is happening in the soil. Why exactly does the water from the lawn sprinkler enter the soil, not just puddle on top? Okay, sometimes there are exceptions, as you see where this unfortunate soul is moving water with not much luck. One might answer that gravity pulls the water down, but then why can you water a houseplant by setting it in a pan of water, asking the water to move up? Does the homeowner with the sandy soil water as much or as often as the one with the clay soil in the yard? I'm Dr. DeBusk, and in this video, we talk about how water behaves in the soil and even the shape of the water molecule. In short, the basics. A number of forces influence the way water behaves in the soil. The most obvious is gravitational force, which pulls water down through the soil. Other forces, called adhesion and cohesion, work against gravity to hold water in the soil. Adhesion is the attraction of soil water to soil particles, while cohesion is the attraction of water molecules to other water molecules. Two water molecules attract because the electrical charge is unequally distributed. The plus side of one molecule attracts the minus side of another, forming a hydrogen bond. This is cohesion. Hydrogen bonding also accounts for adhesion. The main chemical in soil minerals is silica. Silica, with the chemical formula SiO2, has oxygen atoms on its surface that can form hydrogen bonds with soil water. Together, adhesion and cohesion creates a film of water around soil particles. The film has two parts. A thin inner film is held tightly by adhesion. Adhesion water is held so tightly that it cannot move. A thicker outer film of water is held in place by cohesion to the inner film. Cohesion water, or capillary water, is held more loosely, can move in the soil, and some can be absorbed by plants. Thus, plants use cohesion water that is clinging loosely to soil particles. Soil water exists in small spaces in soil as a film around soil particles. Capillary action is shown by movement of water upward against gravity in a capillary tube. The water rises because it is attracted to the glass by adhesion. The thinner the tube, the higher the water column rises. Soil pores can act as capillaries. Capillary action, the additive effect of adhesion and cohesion, holds soil water in small pores against the force of gravity. The fact that soil water can move in directions other than straight down is also due to capillary action, which also explains why you can water a potted plant from below. The smaller the pores, the greater, though slower, the movement can be. Plants obtain moisture by drawing off water from films around soil particles. The difficulty of the process depends on the strength of the force attracting water molecules to soil particles. Soil water potential is the concept used to measure soil water forces. It is defined as the work water can do when it moves from its present state to a pool of pure water in a defined reference state, which is assigned a potential value of 0. More simply, one can think of potential as the tendency of water to flow or move freely in the soil. The higher the water potential, the more freely it can move. The more freely it can move, the more available it is to plants. Consider raindrops falling on a dry soil. This water is capable of great movement, so it has high potential. Infiltration occurs because water will readily move from a state of lower potential, and this occurs when free water enters a pore at the soil surface. Look at the diagram. It shows the energy level or potential of water molecules near a soil particle. The closer a molecule is to a soil particle, the more restricted its movement, the more tightly bound it is, and the lower its potential. Soil water potential consists of the sum of several separate forces. In most soils, the main force is the matrix potential, the potential that results from the attraction of water to soil particles. Matrix potential is always a negative value. Adsorbed water has less ability to do work than free water in a pool, which is defined as 0 potential. Rather than being able to do work must be applied to adsorbed water to move it. A second force is gravitational potential. Soil water is elevated above the water table and so carries potential energy from gravity. To achieve a lower energy state, water simply percolates through the soil to a lower elevation. Gravitational potential is usually a positive value. The third force, osmotic potential, is most important in soils of high salt content. Because water molecules are polar, they are attracted to charged salt ions. For instance, the positive end of a water molecule will be attracted to a negatively charged ion. This attraction lowers water potential. In soils of low salt content, osmotic potential makes a minor contribution to total soil water potential. Osmotic potential is always a negative number because the reference state is pure water without dissolved ions. Potential is represented by the psi symbol. The total water potential is the sum of the gravitational, matrix, and osmotic potentials. The official unit of water potential is the megapascal, MPa, but some still use bar, which is 0.1 megapascals. Soil water potential is usually a negative number because its largest part, the matrix potential, is a negative value. When we say soil water potential is high, we mean the value is less negative. That water is loosely held, able to move readily, and easily available to plants. The figure on the slide shows a water film with bars of potential. The force varies through the film, and the closer to the particle, the larger the negative potential, and the more work must be done to pull the water away. The potential for water in the soil as a whole is expressed as the most weakly held water in the soil. Consider what happens after a heavy rain. At first, soil pores are filled with water. This is called saturation. At saturation, matrix potential is essentially zero, and gravitational potential dominates total water potential. In larger pores, some water is far enough away from the nearest surface that its gravitational potential exceeds matrix potential. That is, the force of gravity can overcome the weak attraction of that water to soil particles, and it will flow downward rather than be held in place. The extra water, called gravitational water, drains through the soil profile, usually within 24 to 48 hours in a well-drained soil. Eventually, drainage ceases. The soil moisture level at that point is called field capacity. At field capacity, water films are thin enough to hold against gravity, and matrix potential now balances gravitational potential. Soil water potential is about negative 1/3 bar. Air fills the interior of large pores while micropores remain water-filled, and thick films of cohesion water surround each soil particle. Plant growth is most rapid at this ideal moisture level because there is enough soil air, yet water is held loosely at high potential. When drainage stops, water removal by plants and evaporation from the soil surface continues to deplete cohesion water, shrinking soil water films. This is the available water. As water films thin, the remaining water clings more tightly, being held at lower potential, larger negative value. It becomes increasingly difficult for plant roots to absorb water. Eventually, at the permanent wilting point, most cohesion water is gone and the plant can no longer overcome the soil water potential. As the wilting point approaches, water becomes stuck in place. It cannot move quickly enough toward the root through the soil to support plant needs. The plant wilts and dies. The potential at this point varies according to plants and conditions, but is usually about negative 15 bars for typical plants. Some desert plants have adaptations that permit them to draw on water at much lower potential. Beyond the wilting point, some cohesion water remains but is unavailable to plants. This point is called the hygroscopic coefficient, the point at which the soil is air dry. Hygroscopic water, as it is called, is held to particles so tightly between negative 31 and negative 10,000 bars that it can be removed only by drying soil in an oven. How much water can a particular soil retain and make available to plants? Actually, these are two separate questions because only the portion of soil water between field capacity and wilting point is available to plants. Both the total water holding capacity and the available water holding capacity are based mainly on soil texture. Sand grains are large, so the internal surface area of a sandy soil is quite low. Thus, there is little surface to hold water films. In addition, pores are large enough that much of the volume of each pore is too far from a surface to retain water against gravity. The opposite is true of clay soils. They have small pores and a large internal surface area. Thus, soils high in sand have a low total water holding capacity, while soils high in clay have a large water holding capacity. Clay particles are crowded together tightly, leaving tiny pores. Any water molecule occupying a pore space will be close to a clay surface. Therefore, it will be tightly bound at low water potential. Sand is the opposite. This leads to two rules. First, water in fine soils is held at low potential and water in coarse soils is held at high potential, so it is easier for plants to remove water in coarse than in fine soils. Second, because most water in high clay soils is held at low potential, much is unavailable to plants. In contrast, most water in a sandy soil is available. To hold the largest amounts of plant available water, soil needs a mixture of large and small pores, with many of the medium-sized pores caused by silt and very fine sand. The figure and table show the effects of texture on soil water retention. Fine sandy loam holds more water than regular sandy loam, reflecting the influence of very fine sand. Clay has the highest total water holding capacity but holds no more available water than a sandy loam. Medium textured soil has the highest available water holding capacity, especially silt loam. Organic matter also influences water retention. For instance, a silt loam with 4% organic matter has twice the capacity of one with 1% organic matter. In coarse soils, organic matter can make a big difference in how much water the soil holds. Thus, the rule that organic matter improves sandy soils partially by improving its water holding capacity. Horticulturalists suggest that young trees be watered by letting a hose trickle on the ground. How will water move into the soil? The figure on the left represents the way water penetrates the soil from a trickling hose. The shaded area shows penetration after 24 hours. The bars show how deep 2 inches of water penetrates for each soil texture. The figure shows that water percolates more slowly and less deeply in the clay loam, but moves further laterally. Saturated flow downward is the movement of gravitational water, usually percolation. It occurs most rapidly in coarse soils with large pores. Unsaturated flow is the movement of water from moist to dry soil, high to low potential, by capillary action in any direction. Large pores in sand inhibit unsaturated flow. The top photo shows that water advances into the soil with a definite wetting front, wet behind a distinct line, dry ahead of it. In dry soil, water cannot move forward until films behind the front are so thick that soil particles let go of the water. Behind the front, soil is nearly saturated. Immediately ahead of the front, soil is still unwetted. One cannot half-wet a soil volume. Either all of a soil is wet, or else part is wet and part is dry. To water plants properly, growers must understand this fact. Water moves upward in the soil as surface layers dry, moving from areas of high potential to areas of low potential. This upward movement is called capillary rise. The sub-irrigation of the bottom photo depends on capillary rise to deliver water into the root zone of the tomato plants. Because of capillary rise, soil water can evaporate from the soil surface. When the surface dries, cohesive films become too thin for capillary flow, so upward migration almost halts. This creates a sharp boundary between the dry surface and a moister soil below. The boundary protects against further rapid moisture loss. One method of irrigation makes use of capillary rise. Some greenhouse potted plants are even watered from below by placing pots on benches that can be flooded. In dry climates or in potted plants, as water rises to the surface, it carries dissolved salts with it. These salts are left behind when water evaporates, so they build up in the root zone. The problem is countered by overwatering slightly during irrigation, washing excess salts deeper into the soil or out of the pot. Normal soil profiles contain horizons that may differ in texture. What happens when percolating water meets the boundary between two horizons of very different character? In the figure, water percolating through a fine-textured horizon encounters a coarser soil layer. One might expect that percolation would speed up because of the larger pores of the coarse layer. The soil would become more droughty. In fact, percolation slows down. As the figure shows, water does not enter the coarser layer at first, but instead spreads out along the boundary. Why? Recall that water is being pulled down by capillarity as well as being pushed down by gravity. The large non-capillary sized pores of the coarse layer exert much less pull on the advancing water than do the fine pores above the boundary, so the clay will not let go of the water. Or put differently, water tends to move from large pores into smaller pores because of matrix forces. Small pores do not let go of the water into large pores. Because water is more strongly attracted to clay than sand, the front spreads rather than being pulled across the boundary. When the topsoil is almost saturated, its potential is high enough that gravity can pull water downward into the sand. Commonly, the A horizon is coarser than the B, so a sharp boundary exists between a coarser upper layer and a finer lower layer. As expected, the finer pores pull the water down. However, because water naturally drains more slowly through fine soils with their lower hydraulic conductivity, water will still build up above the fine textured layer. Any sharp boundary between two layers of dissimilar texture retards drainage. This may be helpful because it can improve the water holding capacity of a topsoil. In some situations, though, slow drainage may keep the upper soil saturated long enough to injure roots. We sometimes call this perching the water. Landscapers encounter and sometimes create these interfaces between different textures. An example is top dressing a yard with black dirt before laying sod, which may be more damaging than helpful. The rule here is to mix the top dressing into the soil to avoid the sharp boundary. Golf greens may be designed to hold moisture by creating layers. A 12-inch layer of special root zone mix is laid atop a 2-inch layer of sand over a 4-inch layer of pea gravel over drain tile. The design causes a wet zone to develop above the sand so turf roots are watered from below by capillary action. If the root zone gets too wet, excess moisture drains into the pea gravel and is removed from the green. Besides saturated and unsaturated flow, water can move through the soil by preferential flow. Under saturated soil conditions, as occurs during heavy rains, water may encounter biopores or other soil channels and quickly enter the channel and flow downward under the force of gravity deeper into the soil profile. Water enters channels under two conditions. If the channel opens to the surface where water is ponding, as in a heavy rain, water simply flows in. If the channel does not open to the surface, matrix forces prevent filling of the channel until the surrounding soil is saturated. Once pores are full of water, the matrix potential goes to zero and water can be released into the channel. Because tillage reduces the number of channels and erases their entry at the surface, preferential flow will be most important in undisturbed soils and under reduced tillage or mulches. Preferential flow can greatly increase infiltration and percolation, reducing runoff and allowing deeper penetration of water. It can also mean deeper penetration of pollutants such as pesticides because the water bypasses the filtering action of the soil matrix. Uptake of water by plant roots is also governed by soil water potential. If water potential inside a root is lower than the surrounding soil water potential, then water flows into the root across the cell membrane. As a root hair removes water from a pore, potential falls at that point and water in nearby thicker films flows towards the low potential site where the root is withdrawing water. A plant can be compared to an unbroken column of water, beginning in the soil volume that supplies water to a root and ending in the air outside the leaves. Normally, the driest end of this column, the lowest water potential, is the air. The potential of water vapor depends on relative humidity and is always at relatively low potential unless the relative humidity approaches 100%. The wettest end, highest potential, is the soil. Water moves into roots, up the stems, into the leaves, and out into the air, high to low potential. Water transpires out of the leaf into the drier air, making the leaf drier. That water is replaced by water from the stem, which becomes drier, and so on down the stem into the roots. Water in roots is replaced from the soil. In saline soils, the potential is even lower due to the osmotic potential, and water can actually be drawn out of the roots even in moist soil. Most plants get the bulk of their water from near the soil surface. Corn, a relatively deep-rooted plant, gets 40% of its water from the top foot, 30% from the next foot, and 20% from the 2 to 3 foot depth. When the soil is deep and there is no restriction to rooting depth. The depth being exploited by the plant also varies over time as the soil dries or is moistened by rain or irrigation. When the whole rooting zone is moist, the plant draws mainly from soil near the surface. As the surface dries, the plant begins to draw more heavily from deeper soil. If surface soil is kept moist enough, then the plant is well supplied by near-surface water. Top growth is favored over root growth, and plants will tend to have shallower, sparser root systems. The plant is unable to exploit lower soil levels quickly when the surface dries and is therefore vulnerable to drought. Proper irrigation wets most of the rooting depth of the crop and allows for some drying between waterings. Another aspect of root growth also emphasizes the need for constant root development. As roots grow at the tip, the most actively absorbing zone, including root hairs just behind the tip, also advances further into the soil. Older parts left behind lose their root hairs and absorb less readily. If older root tissue is not replaced by younger, uptake of water and nutrients become less efficient. So far, this video has concentrated on water behavior in the soil. There it moves in response to differentials in gravitational, matrix, and osmotic potential. However, water that lands on the soil but fails to enter the soil collects on the surface to form puddles. We call this ponding. It moves in response to gravitational potential only, that is, downslope. Anytime water ponds on the soil surface, it can move and carry with it soil and pollutants. When water moves, it leaves one place drier and goes to another place that becomes wetter, possibly too wet for good plant growth or even contributing to flooding. The physics of it dictate that water will flow down the steepest gradient available to it. The top figure shows water flow and contour lines of the landscape. The contour lines are imaginary lines that remain at constant elevation. This land generally slopes downhill from upper right to lower left. Water runs perpendicular to the lines as shown by the arrows. Water flow concentrates where opposing contours meet. Under certain circumstances, water also flows downslope in the soil. Soil layers tend to follow the topography, so on a slope where the soil is wetter than field capacity, water will slowly flow through the soil in a downhill direction. This is particularly true when a subsoil layer perches water above it. The water will flow downhill just above the layer. It may come to the surface somewhere downslope as a seep. In conclusion, soil water potential dictates the behavior of water in the soil. Fine textured soils have the highest water holding capacity, but medium textured soils retain the greatest available water. Transpiration is greatly affected by water potentials and is how the plant absorbs water.